Working with normally distributed variables. Determine a percentage or probability for a normally distributed variable. Step 1. Sketch the normal curve associated with the variable. Step 2. Shade the region of interest and mark its delimiting x value or values. Step 3. Find the z-scores for the delimiting x values found in Step 2. Step 4. Use the standard normal table to find the area under the standard normal curve delimited by the z-scores found in Step 3. Example: a variable is normally distributed with a mean 7 and a standard deviation 2. Find the percentage of all possible values of the variable that lie between 2 and 9. First thing we know is that we have a mean of 7 and a standard normal curve. And we know that we have x values 2 and 9. So we want to use z equals x minus the mean divided by the standard deviation to convert these values to z-scores. Starting with the 2, I have z equals 2 minus 7 divided by 2, and that gives us a negative 2.5. Using the standard normal distribution table, I find that a z-score of negative 2.5 has an area of 0.0062. Next, I'm going to find a z-score using 9 for x. 9 minus 7 divided by 2 equals 1. I can go to my standard normal distribution table and find that the area that corresponds to a z-score of 1.00 is 0.8413. Now I need to subtract my two areas, and that will give me 0.8351, which gives us a percentage of 83.51%. I could have also used my calculator. Stat, DISTR, go down to normal CDF, enter, type in my lower value for my z-score, which was negative 2.5, my upper value for my z-score, which was 1, enter, and I got the same area, 0.8351. Example: a variable is normally distributed with a mean of 7 and a standard deviation of 2. Find the percentage of all possible values of the variable that exceed 6. So I'm going to draw a picture. It's the same as before with a mean of 7 and a standard normal curve. 6 is to the left of 7. So I'm going to substitute into my z-score formula. Z equals 6 minus 7 divided by 2, which gives me a negative 0.5. I can use my table to find the area that corresponds to negative 0.5, which is 0.3085. 1 minus 0.3085 gives us an area of 0.6915. which is 69.15%. So the percentage of all possible values of the variable that exceeds 6 is 69.15%. Example: a variable is normally distributed with a mean 7 and standard deviation 2. Find the percentage of all possible values of the variable that are less than 3. So we have our normal distribution with our mean 7 again. This time our number 3 is to the left of 7. Using my z-score formula, I substitute z equals 3 minus 7 divided by 2, which gives us negative 2. The area for negative 2.00 is 0.0228. Since that's to the left, I can go straight to my percentage of 2.28. Empirical rule for variables. For any variable whose distribution is bell-shaped, in particular for any normally distributed variable, the following three properties hold. Property 1. Approximately 68% of all possible observations lie within one standard deviation to either side of the mean. That is, between mean minus one standard deviation and the mean plus one standard deviation. Property 2. Approximately 95% of all observations lie within two standard deviations to either side of the mean. That is, between the mean minus two standard deviations and the mean plus two standard deviations. Property 3. Approximately 99.7% of all possible observations lie within three standard deviations to either side of the mean. That is, between the mean minus 3 times the standard deviation and the mean plus 3 times the standard deviation. Example: apply the empirical rule to complete each sentence. According to a study, brain weights of men in country A are normally distributed with mean 1.42 kilograms and standard deviation of 0.12 kilograms. Approximately 68% of the men have brain weights between. We want to use our empirical rule to solve this problem. Because we're looking at 68%, that's within one standard deviation of the mean. So we want to find mean minus the standard deviation and mean plus the standard deviation. Substituting 1.42 minus 0.12 is 1.3. 1.42 plus 0.12 is 1.54. Approximately 68% of the men have brain weights between 1.3 kilograms and 1.54 kilograms. Example: apply the empirical rule to complete each sentence. According to a study, brain weights of men in country A are normally distributed with mean 1.42 kilograms and standard deviation of 0.12 kilograms. Approximately 95% of the men have brain weights between. Going to our empirical rule, 95% is within two standard deviations of the mean. So we want to find mean minus 2 times the standard deviation and the mean plus 2 times the standard deviation. Substituting 1.42 minus 2 times 0.12, which gives us 1.18, and 1.42 plus 2 times 0.12 is 1.66. Approximately 95% of the men have brain weights between 1.18 kilograms and 1.66 kilograms. Example: apply the empirical rule to complete each sentence. According to a study, brain weights of men in country A are normally distributed with mean 1.42 kilograms and standard deviation of 0.12 kilograms. Approximately 99.7% of the men have brain weights between. Using our empirical rule, we know that 99.7% of our data is between three standard deviations of the mean, which is the mean minus 3 times the standard deviation and the mean plus 3 times the standard deviation. Substituting, we have 1.42 minus 3 times 0.12, which is 1.06, and 1.42 plus 3 times 0.12, which is 1.78. Approximately 99.7% of the men have brain weights between 1.06 kilograms and 1.78 kilograms. Determine the observations corresponding to a specified percentage or probability for a normally distributed variable. Step 1. Sketch the normal curve associated with the variable. Step 2. Shade the region of interest. Step 3. Use the standard normal table to determine the z-scores delimiting the region found in Step 2. Step 4. Find the x values having the z-scores found in Step 3. The formula is x equals the mean plus z times the standard deviation. Example: a variable is normally distributed with mean 9 and standard deviation 3. Find the first quartile Q1. First thing I want to do is draw my standard normal curve. I've marked my mean, 9, and we want to find the first quartile. Our formula is x equals the mean plus z times the standard deviation. We need z in order to use our formula. Finding the first quartile means we have an area of 25% because that's a quarter of our data. 25% is an area of 0.25. Going to our calculator, we want to go to our distribution menu, second, VARS. We want number 3, which is inverse norm. Our area is 0.25. We want to leave our mean as 0 and our standard deviation as 1. We are using this instead of the table. Press enter, enter again, and we get negative 0.67. Our z-score is negative 0.67. Substituting into our formula, we have x equals 9 plus negative 0.67 times 3, which gives us 6.99, which is the maximum value for x for the first quartile. Example: a variable is normally distributed with mean 9 and standard deviation 3. Find the third quartile Q3. We have the same mean and standard deviation as the previous example. We also want to use the same formula. This time, when they tell us we have 3 quartiles, that means our area under the curve is going to be 75% of the data, which means that A equals 0.75. To find Z, we want to calculate. Second, distribution menu, we want the third one down. This time our area is 0.75. Enter, and we get 0.67. So Z equals 0.67. Substituting, x equals 9 plus 0.67 times 3, which gives us 11.01. Example: a variable is normally distributed with mean 9 and standard deviation 3. Find the 90th percentile. Again, we want to draw our standard normal distribution and use our same formula, x equals mean plus z times the standard deviation. Since it's the 90th percentile, that means our area is 90%. So A equals 0.90. We need to calculate. This time I'm going to use second, enter, which retypes what I just entered. I'm going to arrow over and change 75 to 90. So I want inverse norm of 0.9. Also, 0 as the mean and 1 as the standard deviation is the default. So if I have just inverse norm 0.9, I'll find my z-score. Enter, and we get 1.28. Z equals 1.28. Substituting into our formula, x equals 9 plus 1.28 times 3, which gives us 12.84. Recapping, working with normally distributed variables. Determine a percentage or probability for a normally distributed variable. This is where we use z equals x minus the mean divided by the standard deviation to take our data and change it to a z-score. Once we find our z-score, we find the area that matches our z-score, which is either our probability or we can change it to a percentage. Empirical rule for variables: 68% of the data is within one standard deviation, 95% of the data is within two standard deviations, and 99.7% of the data is within three standard deviations. Determine the observations corresponding to a specified percentage or probability for a normally distributed variable. This is where we're given the area, we find its corresponding z-score, then use x equals the mean plus z times the standard deviation to find our data point.